Here the couplings are weak. Eventually the couplings become strong and things hadronize. And out of this mess of jets and so on, we have to see the effects of resonances or other activities. But stable in, stable out, nonlinear stable out, and then we have to see from the correlations and how things come out what the new physics was. Well, this has a very precise analog in inflation. The analog of seeing these stable particles, you see a stable particle is measuring a propagator. It's a 2-point function. Right? So measuring the power spectrum is measuring the 2-point function. That tells us that the particle is there. What we need to do is see the analog of these collisions. Now, unfortunately, unlike at accelerators, we don't get to choose the initial state. But fortunately, there is some fluctuations in de Sitter space that give us the fluctuations to begin with. And these guys can bang into each other, produce new particles, come back out. Just like here the underlying couplings are weak and they become strong at larger distances. Exactly the same thing is true here. The underlying couplings are very weak. That's actually the unfortunate thing. The couplings here are suppressed by h over n Planck. It's around 10 to the minus 6. So instead of being 0.1, the underlying couplings are 10 to the minus 6. But still, it happens every now and then. And also, at very, very long distances, it becomes strongly coupled. These are perturbations in the clock, which eventually turn into the density perturbations, which are the galaxies and everything else that we see around us today. The analog of jets in cosmology is the formation of galaxies and everything else that we see. And out of this data, we should be able to start learning the rules for reconstructing whether we've made new particles with masses comparable to a Hubble during inflation by looking at non-Gaussian patterns in the sky. People have done a lot of work on looking at various kinds of non-Gaussianity. I think the sort of new and interesting thing here, and this is some just preliminary thoughts that I started to discuss with Juan Alcina, is to look for fingerprints of particles. How do you know you've discovered a particle? What does it mean to see a resonance? Well, what are the rules for how do you disentangle out of this information the stuff that might actually be on it? All right, so that's what I want to say about inflation. Let me just close this part of the talk, and I'm in big trouble. But just by saying that this, in my view, behavior and inflation are, first, they're obviously conceptually related, and they're the triumphant last chapters of 20th century physics. We learned these big rules about how relativity and quantum mechanics control how the way the world works. We pushed them into territory far, far beyond the territory where the ideas were first invented, and they keep working everywhere we go. But in a sense, that's in conceptually understood territory. The real challenges of the 21st century are something else. They go back to the very, very beginning. We said we live in a big space-time with light elementary particles governed by quantum mechanical laws. But why and how? The questions that we now ask are different ones. They're more structural ones. Where did this setup come from to begin with? And what's kind of astonishing is that not only don't we have good answers, in many ways it seems impossible that these things should actually exist. And yet they do. So the two really big questions are, first, we know that space-time doesn't actually make sense. We know that space-time somehow has to be emergent to more primitive degrees of freedom because of famous issues involving quantum mechanics and gravity. So everyone says that. Something fewer people say, but at least I believe is true, is that questions about cosmology in an accelerating universe are starting to expose limitations of quantum mechanics. I'm not saying something crackpotish like quantum mechanics is wrong. I'm saying that there are cosmological questions and places where we don't even know how to use the rules of quantum mechanics. So that means that these two big principles on which everything rests and which make the universe inevitable, both of them are suspect. One of them almost certainly. The other one, at least there are places where it's starting to cry unquote. Wow, he's a great guy. Thank you. Okay. And secondly is the question, why is there a big universe? Why is there a big universe to begin with? The largest of the universe is something we don't understand. That's another way of saying the cosmological constant problem. By all rights, the vacuum energy should have been Planckian, and then there would be no big universe to talk about, nothing to scatter, no asymptotic regions, everything would be crumpled up on the Planck scale. Okay? And why does it have big things in it? The reason why the universe has large things in it is because gravity is so weak. If gravity was much stronger, everything would be crunched to microscopic black holes. So why the universe is big with big things in it is the hierarchy problem. And it's astonishing that after all these amazing successes, we don't understand where the zeroth order starting point could come from. In fact, it seems if you handed a bunch of theorists the Lagrangian or the Standard Model, and you first told them the universe is flat, right? It is flat, it's big, go on and calculate and say, great, everything is awesome, G minus 2 to the 12 decimal point, everything is great. Then they step back and say, was that reasonable to begin with? That was crazy to begin with. It should never have looked like that to begin with. That's the paradoxical situation that we find ourselves in. And so indeed, I think the central questions today are not about details, but concern structural questions about the origin of space-time and our macroscopic universe. I want to stress again that the discovery of the Higgs is a crucial part of this story, of what's so strange. Had we seen something like Technicolor, it would have been, to my mind, much more boring. We've seen things like Technicolor everywhere else in physics before. Everywhere we've generated large hierarchies of scales, it's worked in that way. In every crappy metal that generates large hierarchies of scale, it works that way. If our universe looked like that, it would be interesting because it's the vacuum of our universe, but it would not be conceptually different than anything our condensed matter friends do in their labs. And what they do is cheaper, they get a much bigger variety of systems that they study, and so our universe would not look particularly more special than what they study in their labs. That's not what happened. They've never seen something like the Higgs in their labs. Okay? Except when there's someone out there fiddling the dials, finally adjusting the parameters in order to make it light scalar. That's indeed one of the reasons why Ken Wilson suggested this idea of naturalness, because to explain why you don't walk around seeing random condensed matter systems with light scalars, because it takes fine-tuning to get light scalars absent another mechanism. So the fact that we have this big universe that calls modular constant, the fact that we have a light Higgs for both of these questions, it's pushing us up against things that we've never seen before. So, so I don't have that much time, but I just want to say a few words about what at least in my view, this sort of 10, 20, 30, 40-year experimental future should be, which is motivated directly by these biggest questions. There are zillions of questions, very interesting other questions, okay? But of these two very major questions, this understanding of why there's a macroscopic universe, what, if anything, controls these violent quantum mechanical fluctuations of the vacuum? More and more violent at shorter and shorter distances that would want to destroy long-range order, and yet here we are, the universe big with nice long-range order. What controls them? Does anything control them? Maybe nothing controls them. Everything that we can learn about the quantum fluctuations in the vacuum that affects the Higgs in particular is going to shed some deep light on this question. And I think if you care about that question paramountly, then the experimental future revolves around great big circular colliders, 100-kilometer tunnels, which can run a Higgs factory at low energies to do precision Higgs measurements, and eventually get to the energy frontier in proton-proton collisions. Now, I just want to spend a few minutes talking about this, and I'll end. I'm going to spend a few minutes talking about physics motivations for these machines, but I should say that at least in my view, it's the absolute obvious future thinking about these big machines related to very big physics ideas. Has been the lifeblood of our field for a long time. And we should go there because human beings know how to go there. We are thinking about doing it before with the SSC, virtually the same machine, so we know we can do it. If we can go there, we should go there and see what's there. That's the most zeroth order reason for it. But in more detail, how to proceed will depend on first of all 13 results. But in every scenario I can imagine, we're going to need these machines. And this is not a trivial statement. This is not just the first statement, rah, 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 we should go no matter what. That's also a good argument. But it's not that. In fact, had things evolved in TeV scale physics the way many of us imagined that it would in the mid-1990s. The vision of the mid-1990s was that the LHC would discover 300 GeV gluinos, would make gluino a second. We would have 10 million gluinos to play with. And so then, what you want to do, you obviously discovered supersymmetry. You want to do very precision measurements of the electroweak sector and learn something about the physics at very high energies. That was the vision. It's a very nice vision. The vision that I was a good foot soldier for myself as a graduate student and a postdoc. But it's not the way things have turned out. Okay? We have not seen 300 GeV gluinos. We haven't seen anything other than the Higgs boson. That does not mean that we're not going to see new physics at the LHC. We very well may see new physics at the LHC. But even if we do, it's not going to be a factory anymore. Okay? We're not going to make zillions and zillions of them. And so, in this picture of the world, no matter what is going on, so in the first picture of the world, you wouldn't necessarily advocate going to 100 TeV. Maybe you say you go there eventually, but you wouldn't necessarily want to do that. You would want to do precision measurements in lower energy plus and minus switches, and that would make perfect sense. But given what's actually happened, no matter what, you're going to need to get to 100 TeV anyway. And that's why I'm saying it's not a trivial statement. So let me just rifle through this. You can go through the slides, and I'm happy to chat with anyone afterwards. But I think the case for these machines rests on three main legs and a fourth bonus. The three main legs are first exploring the physics of unbroken electroweak symmetry, rather than electroweak symmetry breaking, to now understand how exactly electroweak symmetry is restored as a continuation of this great discovery of the Higgs. Secondly, to settle and understand the ultimate fate of naturalness. Third, to give a very robust probe of TeV scale weakly interacting particles that could well be dark matter. As I said, there's many interesting opportunities for flavoring CP, although they're bonus and not making progress. So let me just go through it very quickly. So first, we spent decades asking about what breaks electroweak symmetry. Now we know what breaks it. There's the Higgs. But it's now experimentally really, and of course in the standard model, we know exactly what happens when you go to much higher energies. But it's a very important experimental question to settle how this happens. How is it that electroweak symmetry ultimately gets restored as we go to higher and higher energies, higher and higher temperatures? We'd like to see, we've seen, just the little tiny fluctuations around the potential. We'd like to see what the whole picture of the potential of electroweak symmetry breaking looks like. I think this is something very interesting, because we could finish the whole run of the LHC. We could know the Higgs coupling is at 10%. And it could still be totally compatible with a first-order phase transition for electroweak symmetry breaking in the early years. Okay? So that's not a satisfactory state of affairs, right? So you'd like to be able to know, did we learn enough about the Higgs to be able to confidently talk about what happens as the temperature goes above the weak scale? The answer after the LHC is likely no. And the reason is that it's very easy to imagine particles, even standard model singlet particles that interact with the Higgs, that change what the potential looks like. And if these particles are around, then we want the transfer of the electricity, but they will do two things. Precisely because they have to affect the electroweak transition. They can't be arbitrarily heavy. They have to be light and they have to be strongly enough coupled, which means they necessarily give rise to visible deviations to Higgs couplings at Higgs factory, and the possibility to directly produce these particles at 100 TeV. So I'm not going to have time to go through these things there's some other interesting issues as well. But I don't have time to talk about it. So that's one thing. It would be nice to be able to say experimentally, an experimental fact, we know what the order of the electroweak transition is. We're not going to be able to do it by literally reconstructing the finite temperature conditions at the LHC, but we could probe enough about the couplings of the Higgs and particles that could be affecting the Higgs in order to be able to make this as an experiment. Secondly, there's a question of the fate of naturalness. If we just run the LHC, we don't see anything other than the Higgs, then we will have evidence of fine-tuning at the 1% level. And that's not good. But there are many other instances in physics where we've seen accidents at the 1% level that we have not, has not shaken us to the core of our faith that this general idea of calculus is correct. Why? Because we've looked, there are order 30 parameters. There are many kinds of experiments we could be doing. 1% level accidents in nuclear physics, in all kinds of other places in physics happen, and they're roughly compatible with the look elsewhere effect. So if we see a similar tuning for the Higgs, it won't be conclusive that this idea of natural language is totally wrong. It could be compatible with just being around a percent tuned and having missed the particles. But you can't hide these things either from a Higgs factory or from